Okay, good morning, everyone. I hope you are doing all right. So, last class we started talking about torque, and torque is kind of force companion for rotating object. So, if object is rotating or when object is rotating, it's not just the force matters, rather torque matters. That's what we learned. And we learned three different ways to calculate torque. And then we also learned how the net torque is equal to 0 is rotational equilibrium. So we're going to continue on that equilibrium and then going to move to rotational kinematics today. Okay. So equilibrium, we said when, for the translational equilibrium, we say, okay, when net force is 0, then object is in rotational equilibrium. And when net torque is 0, then so this is translational equilibrium, by the way. I think I said rotational. This is rotational equilibrium condition, okay? So when both of these are satisfied, we call that stable, like static equilibrium. So those are formal language. I also have these in the, next slide. I'll show you. But here, what happens is, like some object, although may be in equilibrium, that equilibrium may be stable or unstable. So for example, here, let's say the object is here somewhere in the, like a bowl, bottom of the bowl sitting there. You push it, you give a push, and then what happens? It rocks back and forth, right? Eventually settles down to this point. So that's why we call it stable, because even after we, let's say, displace it from that equilibrium point, what happens? It comes back to that point eventually. So we call that stable equilibrium. So now, what is unstable equilibrium? So for example, you may be able to make this, stay there, over there at that point if you are very careful, just like you can make it, this thing stand, if you are very careful, okay? But this, if slightly displaced, is not going to come back and stay there. But instead, if I have something like this mass over here, you see, hopefully you can. So this is stable because if I displace this little bit, it comes back to its position. So this is more stable than, let's say, this pen or something like that. So if I need to make that pen more stable, then I need to do larger base. Okay. So that's what stable and unstable means. Stable means even after disturbing a little bit, it comes back to that position, okay? And unstable, if you disturb a little bit, it never comes back. So that's called unstable. And how is that important in our daily life? So when does that happen? How do we know that? Okay. So we talked about center of mass and center of gravity last class. Okay. So if we have big truck loaded with heavy object, then what happens is there is more mass on the upper part of this truck than the lower part. So in that case, what happens is center of mass shifts towards the more mass. So this is center of mass or center of gravity, because for the objects of this side, center of mass and center of gravity going to be same when we are near the Earth's surface. So now the line passing through that is what we call weight. Okay. So if weight of that object is passing through this, under this large base, within the large base, then the object is in equilibrium. But if the center of mass or center of gravity gets out of that base, then what happens? It becomes unstable. So for example, same truck, if you drive in very inclined road, let's say, so in that case, what happens? Now center of mass or center of gravity, this weight line goes something like this. So the weight is outside the base. So that's why it becomes unstable. So that's the reason these, drag racers, they are not so tall. So they want to keep the center of gravity close to the earth, and they want to make base bigger so that it never out of that, even when it's going in very inclined, track, this race track. Okay, so that's the reason. And how do we, let's say, use that in our personal life? So, for example, let's say you are trying to learn some yoga position, and let's say you got interested in this headstand position where you put your head on the floor and feet on the top. So, usual way to do that would be to just try to balance yourself by holding with these hands, right? So maybe if I can briefly stop sharing, you can see it better. Okay. So you can just try, holding this and then lift your leg up. So when you do that, what happens is the base you have available is like something like this, just this much. Okay. But instead, if you do this and like this, then what happens is this base becomes triangular and becomes larger. And at the same time, so this muscle helps you to keep you in balance. Okay. So when I was learning, what I did was I could not do it by just using this hand. But once I tried doing this several times, of course, you have to try several times. It's like solving physics problem. You need to try several times. You need to practice several times. Then I was able to do it. I'm not sure if I can do it now. Okay, sometimes in the class I could do it, but over here I don't think you can see it in camera. But as a part of my exercise for today, let me try that and see if you can see my feet, okay? You can see my feet if I can stand on my head. So let me try that here. Here comes my legs. Okay, can you see it? So I'm tilting a little bit so that it goes in the field of view of camera, even if I'm not. So that's what I learned from physics. And then I was able to do it. Okay. So now see if you can do that. So if you cannot do headstand and if you want to practice, try doing that in past semesters. At least 4 or 5 students told me at the end of semester, like they practiced and they were able to do it. Okay. Not everyone tries and practices. I understand that. But if you are inclined, try doing that and hopefully you'll succeed. Okay. So now, oops. Okay, I'm sharing this back. So were you able to see my legs or feet up in the air? If you did, write yes on the Zoom. Okay. And okay, so it was on the field of view of camera. Good to know that. Thank you for letting me know. So now, this I already talked about, rotational equilibrium. So when net torque is 0, it's rotational equilibrium. When net force is 0, it's translational equilibrium, right? So now we have, let's say, object like this, okay? So it's like a, flat object like this, you apply first on one side and then the other side and try to spin it, right? So something like that. Some rotating disc, or even better, let's say merry-go-round on the park, right? So you push one side. If another person is helping, another person pushes on that direction, right? So now, in this case, I'm not asking about the torque, but the net force, okay? So how do you find net force? What is the net force? Okay, maybe I can make a clicker question here so that everyone participates. So let me start clicker, and go ahead, you too start clicker. And meantime, now you do this and I'll make the clicker question. A, uh, let's see, 2 times F, B, 0, C, R times F, D, 2 times RF, and E, so just F. So what is the net force on this object due to these two forces? So that's what I'm asking, okay? So I'm going to open the poll, and now you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Mostly B, and there is D as well. So B is correct answer in this case because we're talking about net force. Remember, whenever we need to find net force, we draw a free body diagram. So in this case, one is acting up, another one is acting down. And so if we say up as a positive y, so net force, or sum of forces along the y direction, gonna be one gonna be positive F pointing up, and since we chose up as a positive, and now another one is negative F, so that gives us a 0. Okay, so that's great. Now let me slightly modify this question. So how about net torque now? So I changed force to torque, okay? So now I'm opening the poll, and you have a minute and 30 seconds to answer this question. 30 more seconds. and 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. So there are more D's. So that is correct in this case. Uh, so why is that? Because see, the force is perpendicular. So when force is perpendicular, lever arm is same as R. So torque is simply R times F in this case, because lever arm is same as R. So in this case, it's trying to rotate counterclockwise, so that is positive. And now this one is also trying to rotate counterclockwise, so that is positive as well. And at the same time, so this is also perpendicular. So R times F. When it's perpendicular, lever arm and R are same, so it's the similar situation. So that means it is also positive RF. So that makes is positive 2 times RF. So that's why D is correct answer. So what's the message from here? So net force can be 0, but net torque may not be 0. So what is this object doing then? So net force 0 means this is not moving from one place to another place. Let's say this object is not moving, not translating, okay? But net torque not 0 means this is spinning counterclockwise, okay? It is spinning faster and faster and faster. So that's what it means. So how do we know something is in translational equilibrium? Check if net force is 0, okay? How do we know if something is in rotational equilibrium? Check if net torque is 0, okay? So that's the main thing you want to take away from this slide. And I have written all those things since I already, described this. I'm not going to do that. So net force 0 is often written as the sum of forces along the x and y direction 0. Okay. So when something is in equilibrium, we said in the past, that means it was translational equilibrium only. So we use these two conditions. So now if object is also in rotational equilibrium, that means net torque is 0. So that means we can write this equation as well. So if something is not rotating or not moving, then it is in both kind of equilibrium. So we can use all three equations to solve problem for this kind of situation. And this is called static equilibrium, by the way. Okay. Static equilibrium. When object is in both let's say translational and rotational equilibrium. Okay, so that's the equilibrium. So that means to use this condition, of course, we already learned this in dynamics or laws of motion. So now to use this, we know we need to calculate net torque or sum of the torques. Okay. So what do? You find the torque due to each forces and add them together. And remember, to draw a free body diagram, we draw a line and show the forces, mark the axis of rotation, and from there we calculate the net torque. So here is one question for you. So axis is shown and this distance is given as a r. This is halfway r over 2. This is all the way r. Okay, so those distances are given. So from there, you should be able to figure out labor arm and forces are there. So that means you should be able to find torque. And this also tells you that clockwise is negative torque and counterclockwise is positive torque. So using all these convention, what is the net torque acting on this object? And here are the choices. So go ahead, find the torque due to F, this 2F, this 2F, and add them together. So torque 1, let's say, torque 2, torque 3. So you need to add them with Remember, they have also positive and negative sign depending on their uh, yeah direction, and we learn how to find the direction of torque last class. So sum of torque means this. So you want to calculate this and add them, okay? So you have 2 minutes to answer this question. Go ahead, find torque due to each of those and add them and choose the answer. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay. So in this case, torque due to this force is how much? So it is trying to rotate this way, means this clockwise, that's negative. And this is also doing the same, so negative, but this is on the other side. So that is positive. Okay. So now torque due to this force, so torque 1 is negative, and since the force is perpendicular to this R, labor arm going to be same as R, means it's going to be negative R times F, and same thing goes with this, so negative R over 2 times 2F. Now this one is trying to rotate counterclockwise, means it's a positive, so and its labor arm is R, and force itself is 2 times F. So now we need to add these. So there is 2, that cancels. So there is negative RF, and there is negative RF that survives there, and positive R times 2F means 2 times RF. So it looks like this is going to add to 0. So C is the correct answer in this case. Okay. Okay, so we had varieties of answer here. So that's how you calculate torque due to each of the force. Remember, when force is perpendicular, it is the easiest to calculate torques. Now, we're going to look at one example. So here I'm going to show you systematically how to use this equilibrium condition to solve any problem, okay? And I'll ask you a question directly, very similar to this one over here. That was also in the MCAT example, okay? So what happens? Our head, we are keeping our head straight because the muscle over here is applying some sort of force. Here it says muscle force, okay? And when we take a nap, what happens? Oops, this goes down like that because this muscle force goes away. And our pivot is not exactly at the center of mass of our head. Our head is more mass of our head is on the front side from this pivot than the back side. So that's why this muscle, the force from the muscle is needed to keep our head straight. Otherwise, it goes like that, okay? So now in this question is talking the same thing. So this is drawn here, okay, tentative situation. But what I'm going to do is I'm going to draw actually my own free body diagram rather than this one. That's going to look similar, okay? So remember, we replace object by a line, okay? So these numbers are there, so that's why I did not list the knowns and unknowns. But before I even list the knowns and unknowns, I like to draw my free body diagram in this case. And I replace object by a line and then draw forces. So in this case, there is a weight of our head because center of gravity or center of mass is somewhere here, and it says 50 Newton. Its notation is W. So let's say that force is. So I like to write forces like F. Let's say F1 is W, which is known 50 Newton. Okay. So any force that's given, you can always write one as a F1, F2, simply F, something like that. Okay. And then there is another force from this joint support here, right? So that is going up. And let's say that is simply F. Okay. And there is muscle force that's coming down. Let's say that is F2. Okay. Now, what happens is this is in static equilibrium. So that means net force is also zero, net torque is also zero. So when we have this kind of equilibrium situation, when something is in rotational equilibrium, we are free to choose whatever axis we like to choose. Okay. So in this problem, it doesn't say where the axis is. So here is the thing. If you choose axis wisely, then you're going to eliminate one of the term from the equation, okay? Because you want to make a lever arm for the force zero. Which force? The force we don't know and we don't want or we don't care, okay? So in part A, it's asking us to calculate the force exerted by the muscles using the information in the figure, okay? Force exerted by the muscle, so that means we are looking for this. So we are looking for F2, okay? How about F? For part A, F, we don't know and we don't care. So when you have that particular force, see here, we know it, so we do not want to eliminate W. So that's why you do not want to choose the axis of rotation here, okay? So that's why this is the good choice for the axis in this case. So what happens? Once you have this line of force passing through the axis means lever arm is zero, means torque is zero. So torque due to this force is going to be zero. So when we do sum of the torque, that force not going to be in the equation, okay? So with that, now also label the lever arms, right? So this force is perpendicular to this. So that means this is going to be the lever arm for that force, say L1. And for force 2, I'm writing L2. I was choosing these F1 and F2 so that I could use L1 and L2, something like that. You know, they rhyme. So F over here, we don't want, we don't care. So don't know, don't care. So that's why, see, the lever arm for F, L is zero. Lever arm for the F is zero because this line of action of force is passing through that point. Okay. So now with that, so to solve A, what we want to do is, since the head or the object is in rotational equilibrium, we can write net torque is equal to 0. So now labor arm for force 1 is L1 and the force is F1. And see, it is trying to rotate this way, means that is clockwise, so negative. Okay. And then L2, F2 is the torque due to this. And by the way, sometimes I see student, mixes force and torque. So that means they may simply write F1 here without the lever arm. So if you're not writing lever arm, that means you are just writing force, not torque. So one is torque, another one is force. You cannot just add them, okay? So keep that in mind. So this is about torque. Torque has both lever arm and the force. So make sure those multiplication things exist in the equation. And see how I'm writing this in terms of notation rather than, the number themselves. I wouldn't rush to put the numbers, okay? And this one, torque due to that one is 0. So that's the sum of the torque. So this is the torque due to three forces, okay? Or I can say, to make this thing a little bit more clear, if you like, you can write this, okay? But this term 0, so you can just even ignore and just write these two, okay? So that's the left hand side. So it's like a sum of force, but it's not just force, but the torque, sum of torques. And right hand side is 0 because it is in rotational equilibrium. So now what are we looking for here? We are looking for F2, right? We are looking for F2. We know everything else. For example, what is L1? L1 is this 2.5 centimeter. And since both of them are in centimeter, they're going to get in the ratio and cancel. I don't need to convert that in meters. Yes, if you like, you can convert it, but I don't have to. You don't have to in this case. So this is 5 centimeter. So that means now I'm looking for F2. So F2 is here. So let's move this term to the other side. So it's going to be L2, F2 is L1, F1. So this is negative on this side. So when it goes to the other side, it becomes positive. So that's why F2 is L1 F1 over L2. See how L1 and L2, they are in ratio. So their unit cancels no matter what unit they have, but we have to have same unit. So here centimeter for L1 and centimeter for L2. So that's good. Okay. So with that, what happens is that it is 2.5 centimeter divided by 5.0 centimeter times F1 is 50 Newton. So this is half of 50 is 25 Newton. Okay. So looks like looking at this, it is 1 sig fig. So this is going to be rounded to 30 Newton. Okay. After rounding, it's going to be 30 Newton. But we know in 2 sig fig, it is 25 Newton. So if we need this for further calculation, we can use 25 Newton. Okay, so that's part A. Now, there is part 2. Okay, so I'm going to make room here on this side for part B. In part B, it's asking us what's the force exerted by pivot, and we said that is F. Okay, F is what? So now you see here, what happens is there are 3 forces acting, and out of those, now we know 2. So we should be able to calculate third just by using translational equilibrium. We don't need to use rotational. Using translational is easier than the rotational equilibrium because translational only involves force, but rotational involves torque and torque. That means lever arm and force, right? So sometimes calculating lever arm could be tricky, but how do we draw free body diagram to use the rotation, let's say translational equilibrium? So since we know 2 out of 3 forces, we can use sum of forces along y direction 0. Okay, so let's draw a free body diagram. So this F we want, and remember these two, F2 and F1, they are pointing down. For to use translational equilibrium, we just replace object by a dot and draw a free body diagram. And we are, let's say, if we say up as a positive y, we can now use this equation here. Okay, so I'm kind of running out of room here, so I'm gonna go over there. Okay, so sum of forces, so there are 3 forces. Out of those, F is positive, and F2 and F1, they are negative, so that's the sum of the forces. And right hand side of this equation is 0, so that's why we write that 0. So we are solving for F. So let's move this to the other side. Both of them are negative on the left side, so they're going to be positive on that. So now 50 plus 25 is 75 Newton. Okay, and if you round to 1 sig fig, this is going to be 80 Newton. So that's how we can use both. To solve some problem, we can use both. We have to use both rotational and translational equilibrium. Okay. In some cases, we may just get away by just calculating or using rotational equilibrium. For example, in this case, if just this force was asked, then we could have just used this. But since we can write up to 3 equations, we can solve for up to 3 unknowns. But since there are no forces in the x direction, the equation in the x direction out of question. So that's why we can just use 2 equations here out of 3. Which 3? Remember, out of 3 I'm talking about these 2 and this. So if there are no forces in the x direction, you cannot use that. So that means these 2 you can use, right? So that's what I did to solve this problem. Now, here you can just use one equation, rotational equilibrium, okay? So in this case, there is seesaw, and there are kids and the dad sitting, right? Grawl has a mass of, so Grawl has mass, let's say lower mass, lower m, 30 kilogram. So what's the force? So force due to Grawl, let's say F1 is mg. So now you can just multiply by g and get the F1. Similarly, for the father, it is F2, and this is, let's say, uppercase M times G, where uppercase M is 90 kilogram. So this G may cancel later once you solve the equation, so you may not even have to plug in G, but force is not mass. Remember, force is mass times G. So that's what I'm doing here. So Grawl is sitting here, and it says 2 meters from the fulcrum. So that's where the fulcrum is, right? So that's why so that's the point where the fulcrum is. So let's say, when you sit on that, uh, it's often horizontal at the beginning. So the force is vertical. So you can say, okay, the lever arm in this case is L1, which is 2 meter. If we choose this as an axis, because we don't know how much force the fulcrum is applying, and so we want to choose this as axis. And father sits somewhere here, let's say L2. Where must father sit to balance the seesaw if he has a mass of 92? So let's try to calculate that from the fulcrum, okay? Once we know this distance, we also know how far the father is from the daughter or girl, right? So we can do that. So let's find L2. So over here, we know both forces. This force, once we choose axis of rotation, what happens is we don't need to include that. Okay, so that becomes 0, just like we saw. So we can just use rotational equilibrium in this case, okay? So rotational equilibrium torque is 0. So now go ahead and use this condition to find or solve this problem. Oh, I almost solved that problem. So I'm opening the pool and you have 2 minutes to complete this, okay? And 2 meter is 200 centimeter, just in case. Looks like answers are in centimeters. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So let's see what we got here. So mostly B, right? So B is 67. So dad is 3 times heavier than girl. So that means dad has to sit only 1/3 from the girl. Okay. I mean, this L2 gonna be only 1/3. And 67 makes sense. Okay. So how do I do systematically? So L1, F1, this is trying to rotate clockwise. Oh, hold on, counterclockwise. So this is positive, and that is trying to rotate clockwise, so negative. So L2, F2, And this one does not produce any torque since we are choosing axis over there. So this must be 0. So that means L2 must be equal to, so if we bring this to other side, becomes positive. So that means it is L1F over L2. See how this is just the ratio of, this is supposed to be F1, by the way. See how this is it depends on the ratio, right, of that. Okay. So here L1 is 200. Oh, hold on. What am I doing here? L1, F1 over F2. Now force is in ratio. So F2 is that's mass or the weight due to that. So because of that, it is 3 times more than this. So when you divide by 3 times, it becomes 1/3. So that's what's happening here. So F1 is 30 times G and F2 is 90 times G. See how the G cancels, right? So that's how we see this is just 1/3 of 200 centimeter, which is 67 centimeter from fulcrum. So how about this one? So this is 267. So would be 267 from the girl, not from the fulcrum, okay? So if it was like from girl, then that would also be correct answer. But it says from the fulcrum, so that's why it is not. So yes, it requires a little bit practice of using this. And for the practice, speaking of practice, I have posted a worksheet now, new worksheet. So with this, you should be able to complete that, okay? So second problem is related to this problem, similar to this problem, okay? And first problem, I already talked about in the last class, which is about calculating torque using 3 different methods, okay? So make sure to read question properly and answer the way it is asked, okay? So I want to see you learn all 3 different way of calculating torque. Okay, with that said, now let's move on towards the kinematics, okay? So linear motion and the rotational motion, this slide you have seen in the past as well, part of this slide when we talked about circular motion, okay? And rotational motion. So if we just look at one point in rotational motion, that is a circular motion. So that's why some of these equations work just fine for both circular and the rotational motion. And that's what I'm trying to emphasize here. Let's say I have an object, something like that. It is spinning about that, okay? So if I just look at one point on that object, it's going in circle. So it's like circular motion. So what's the linear distance? That is S, right? And what is angular displacement? That is this, when it goes from here to here. And let's say it is moving with constant speed, but velocity is changing because direction is changing. So it is same as what we did in circular motion, okay? So there is this equation that relates the angular displacement and the radial displacement. It comes from the trigonometry, okay? So now I can solve this one for S, so this linear, okay? So when I do that, I get, come on, S is R times delta theta. So this is angular displacement, this is linear distance, angular displacement, and this is radius at which the point is moving, okay? So this is one equation that relates linear thingy with the angular thingy, okay? So this is in formula sheet. Now we want to relate the velocities. So angular velocity is given by delta theta over delta t, right? Angular displacement divided by time interval. And we have done this in the circular motion as well, just to, since we're going to be using here, I am bringing it same thing. So now delta theta can be written as S over R because we want to go from angle to the linear value. So that's what I'm doing here. And I replace delta theta by S over R. Delta T is still in denominator. But now if I pair this distance over time interval, it becomes speed. So this is speed over R. So there is this relationship between linear speed and angular speed, and that is also related through the R, just like we have here. See, it's the R that relates those two things. And similarly, now we can define the angular acceleration. Remember, the acceleration is change in velocity over time. So what is angular acceleration? Change in angular velocity over time. So that's what I'm writing here. The notation is alpha, okay? And change in angular velocity, see here, divided by time interval. So now what I can do is I can make use of, similarly this one here. So omega is V over R. So that means delta omega gonna be delta V over R. So that's what I'm using here. So that's why I'm using that and copying this delta T. So now I can pair this, and that gives us linear acceleration. A is delta V over delta T, right? A versus alpha. See, they may look kind of similar sometimes, but they are different. Okay, so that's that. And now we can relate this linear acceleration and angular acceleration. And again, that's the R, okay? So because of this kind of relationship between angular and linear world, what happens is we can use the same ideas, that those equations, to grow from linear kinematics to angular or rotational kinematics. So these equations, I hope you remember them, right? Of course you do. So now what happens? See the final velocity. So velocity is r times omega. So if I want to write final velocity, then I can do r times omega f, r times omega f. Similarly, I can do r times omega I. And then how about acceleration? R times alpha. And there is time interval. Now what do you see? There is r, there is r, there is r. So this r, this r, this r can be cancelled, giving us omega f is omega I and that. See, that goes into that. So see how they are similar, very similar. See, this is final velocity in linear world, and this is a final velocity in rotational or angular world, okay? This is initial velocity, this is initial velocity. This is acceleration, this is acceleration. And time interval is same no matter what kind of motion we're talking about. See how they are similar, okay? Not exactly same, but similar. And we can write this equation like this as well. Huh. Okay. And the last equation. So displacement here is angular displacement, right? So we do the same thing. So this one without time, okay? These two have time, okay? And this one has final speed, but this one does not. So these are angular. So the angular speed, angular displacement, when it goes once around, what happens? It makes 360 degree. but we want this in radian, which is 2 pi radian. So in one rotation, what is angular displacement? 2 pi radians in one rotation. So if we calculate angular displacement, total angular displacement, for example, let's say you found that as a 4 pi radian, okay, delta theta. What that means? That means it went through 2 revolution. So how do you find that? So to find number of revolution, you're going to be still finding delta theta, but you'll be dividing that delta theta by 2 pi, okay? So if you divide this by 2 pi, what happens? This becomes 2. So number of rotation is 2. So if you are asked to find number of rotation, what do? You still find delta theta and divide that by 2 pi. That's going to give you number of revolution or number of rotations, okay? Okay, so this is a kinematic equation, folks. And here is a question related to, how we can calculate those things using the idea we just talked about. So here I'm bringing very simple question where you bringing your hand straight horizontal to up like that, okay? So that's what happening, okay? So it says, okay, the time interval is 1.5 seconds. So you are standing facing east with your right hand stretched forward horizontally like that here. So that means your initial speed in this case is 0. You are just starting from here and then go like that, right? So your initial speed is 0. So now it says, what is angular displacement of your hand in degrees and in radians? So you go from here to here. So that is theta is 90 degree. So the angular displacement is 90 degree. How about radians? How do I convert degree into radians? I guess I can do this 90 degree. And remember there are 2 pi radians in 360 degree, or if you have learned pi radians in 180 degree, that is also same. So you can do that as well, okay? So 9 times 4 is 34. So 2, 2. So this is pi over 2 radians, okay? So 90 degree is pi over 2 radians. 180 degree is pi radians. And 360 is 2 pi radians. So now it says, what is the average angular velocity in radians per seconds of your hand during the move? So average angular velocity, okay? So average angular velocity is basically that delta theta over time interval. So delta theta we just calculated in radians, pi over 2 radian. And then time interval in this case is 1.5 seconds. It is going to be in denominator, so I'm writing that. So it is pi over 3 radian per second. And by the way, if you want numbers, pi radian is 3.14. You can find that in your calculator as well, okay? Just in case you need whole number. So this is going to be slightly more than 1 radian per second. So now what is the average velocity of your fist during the move if your hand is 48 meter long? Okay. So it's giving us R, 0.48 meters long. Okay. So that is R. So What happens here? It's like on the shoulder, that's your, center. So it goes from here to here, right? So in this process, it says, so the R is 0.48 meters. So it says, what is the average velocity? V average is what? So we know omega average, and we learned that they are related. So V average is R times omega average. So that means 0.48 meters times pi radian, pi over 3 radian over seconds. Okay. So radian is basically fake unit of the angle. It is the ratio of meter and meter. Remember, delta theta we defined was S over R. Both of them have unit meter, meter. When needed, we can include radian. Whenever we don't need to include. So here the unit gonna be meter per second for the average velocity. That makes sense. So it is, you multiply these numbers and you get the average velocity, right? So those are these kinematic quantities for the rotational motion. Now, here is this kinematic equation question where you note down the things and then choose a suitable equation, just like you do for using regular kinematic equations, okay? You note down the known and unknowns, sketch the situation, note down known and unknowns, and then choose a suitable equation. But looks like it is, time for a break. So let's take a break. Once we come back, I'll pull on this one, okay? So I'll see you in 5 minutes. Welcome back. And when we were in break, I kind of note down the things that we know. Yes, mass and R are also given, but they are not in this equation, so that they're not going to be that much helpful to pick the equation. So that's why I'm just noting down the relevant quantities, okay? So now with that said, to solve this problem, which equation would you choose? So that's the question, right? So I'm opening the poll, and now you have 1 minute and 30 seconds to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly B and some A. So in this case, it's asking for how many revolution. Number of revolution depends on delta theta. So that means we should be looking for delta theta. So since delta theta is not there, so this shouldn't be the option, okay? So this one and that one. So this one doesn't have time, but here time is given. So that's why B is the best choice in this case. So just like the kinematic equation, we do the same thing to solve rotational kinematics. Okay. Only the equation looks slightly different. But if you read something like this, final velocity, so for linear case, it's going to be linear velocity v. Here is the angular velocity omega. Okay. Only that's the difference. So final velocity is initial velocity plus acceleration times time interval. So that's the general way of reading any kinematic equation, for example. Okay. So something like that. So they are very similar, and the method of solving them is also similar. So that's why I brought this example. So for example, in this case, we want delta theta, and once we have delta theta, we can divide that by 2 pi to get n. So here, using this equation, delta theta going to be what? See, the initial speed is 0. So that means it's going to be half times alpha is 0.2 radian over second square, and time is squared. Let's write something like this. And time is square means 5.0 square, and unit also get squared. So this cancels s square. So we are just left with radians here, okay? So this is 0.1 times 5 is 25, okay? A radian, or 2.5 radians. Now, what is delta theta then? Let's see if I do that correctly. 25, 2.2 radian per second squared, 2.1. So when you multiply, 25 becomes 2.5. Looks like that is right. So now n is delta theta over 2 pi means, oh, it's going really slow at the beginning, huh? Delta theta is 2.5 radian, and 2 times 3.14 radian for the pi. So radian cancels. The number of revolution is just a number. Okay. So it looks like this is less than 1 revolution. Hopefully I did not make mistake. Half alpha time squared. So yeah, looks like about right. So this fan starts moving really slow. Tick, 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 5 seconds. Only about how much? Quarter? 6, 2.56. Yeah, slightly more than half, less than half revolution. Okay. So that's how we solve kinematics problem in rotational motion. Okay. And we also learn how to use rotational equilibrium. Sum of the torque is 0. How to use that, right? So part of dynamics and kinematics is covered. So now we need to learn how to use this. Okay. So I have problem. Hopefully we can make it today. Okay. So now before we go, here is this question here. So there is a smaller wheel, there is bigger wheel. I'm sure you have noticed that in bicycle. Sometimes this chain gets out from there and you have to put that. And of course, with the gears, there are so many wheels, but the simplest bike you can get has these two wheels. Okay. So this is the angular speed of a smaller one, and this is the angular speed of large one. So the question is, which one is bigger when you are riding the bicycle? Which one is spinning faster? right? Angular speed is spin. So which one is spinning faster? That's the question. So you have a minute and 30 seconds to answer this question. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Okay. So there is a direct message in my Zoom. It says, Professor Dungana, for the last iClicker question, my Wi-Fi was cut out and I was unable to click an answer. I was going to choose B, but the internet did not sync for me. Will I be marked down points for that? Okay. So what happens is I don't do anything here. It is the software. The app takes care of everything. So I don't go and give point because you missed it. So that's why I have put whole thing in the extra credit category here, okay? So if you pull, you are on point. For any reason, if you miss that point. But once, remember, throughout the semester, I may pull like 150, 200 or so on. So missing 4 or 5, even 10, not going to make much difference in terms of your overall point or extra credit. So you don't have to worry too much about it. But of course, if you keep missing, then it's going to make a difference. Okay. I think I shared this at the beginning, but again, thank you for giving me chance to, you know, say that again. Okay, so that's how the clicker works. I don't go and give points. Okay, it's the clicker app that does the work. And you can see that live on your app. Okay, so with that said, so here, let's see what we got as the responses. So mostly C, and that seems to be correct. Smaller one spins faster. So how do I know that? How do you know that? What we know is when bicycle is moving, the speed of this one and speed of that one are same. What is speed? Linear speed. Remember? Everything in the bike, including you rider, we have all same speed. B is same. So now B is R times omega, means omega is B over R. So smaller R makes omega larger. Okay. Smaller r makes omega larger. So mathematically, that's how we tell. But probably you may have that experience of saying, okay, the small one looks spinning really fast. Okay. So in terms of angular speed. But linear speed, everything is moving with the same speed, right? From one point to another point. Another way to look at it, see here, when it spins once, since they are connected, it may even spin twice because by the time it goes from here to here, it may have already gone once and so on. But mathematically, this is how I like to talk, okay? So with that, so now let's move towards the Newton's second law, or the angle, like how do we apply Newton's second law for rotational motion? So simplest situation for rotational motion, for example, whole object may be moving, but we can start thinking, okay, there is just a point that is moving at a distance r. So we are applying force F. When that's the case, torque gonna be R times F for that particular point or the object, right? So this, we know Newton's second law. Yes, we should be writing something like that. But here we are just talking about just one net force, what's the motion due to then one particular force. So I'm writing something like that. So linear, we have force, but the counterpart of force is torque for the rotational motion. So we want to go to the torque, and torque has a R times F. So what we do is we can multiply both sides by R, and this becomes torque. So let's do that. So torque is R times F, means this is going to be R times MA. Okay. So now this is linear, but we want angular. And linear and angular are related by this R times alpha. So that means I want to replace this A by R times alpha. And that's what I'm doing next. So now what you have is R, and there is M and alpha. So instead of just being M times A, like this, now what we have is R square times M times alpha, okay? So this A is equivalent to alpha, so this mass must be equivalent to mr square. So mr square now behaves like an inertia, just like I briefly talked in the last class as well. And we call that rotational inertia a point mass. If we have just a mass m at a distance r, like in this case, we have this rotational inertia mr square. But we may not have just point mass, okay? We may have whole disk. So how do we take account of that kind of thingy? So still, even there are more than one forces acting, we can use like that, but we have to be careful about this rotational inertia, okay? So for that, let's look at a slightly more complicated, but still bit simple idea. So there is this thing that's rotating about this point. So the axis is here, okay? So axis is passing through that point. So something like this, let's say I have this object here, and if I spin something like this, I can say it is rotating about this axis here, the line passing through this, okay? So similar idea here. So we have now four masses. So for each mass, rotational inertia is mr square. So if there are four masses, then what we do is we calculate rotational inertia for each of the masses and add them together. So since there are four masses, we do that, and that is rotational inertia. So if there are more than four masses or just two masses, the process is same. You just keep adding and adding and adding, okay? So overall, in short, you can write like this, but if there are n number, then in general, you can say, okay, I goes from 1 to n. So I could be just 1. If just 1, then this is 1. This one term, if there I goes from 1 to 2, then these 2. When I goes from 1 to 3, these 3. I goes to 1 to 4, just like we saw here. If I goes from 1 to 100, then you're going to have 100 of these terms. So things get a bit complicated, okay? So that's where the calculus comes in handy, and using calculus, we can find the rotational inertia of different kind of shapes? Since we don't use calculus here, I'm not going to be calculating rotational inertia for any objects, but we're going to be tentatively writing the rotational inertia of the some common shapes, okay, uh, by using this kind of argument. And whenever needed, we can find the rotational inertia, formula for rotational inertia written in book, or you can also search in internet, okay? So it's going to have a formula, and I'll tell you what that means pretty soon. So if we have a disk like this, then what do? Is we separate this into several masses. We assume, okay, there are several masses, and we keep adding all of those. And then finally, we calculate using the total mass m. So when we do that, we get the formula for rotational inertia of a disk like this, okay? Or we can have a ring. So that we can find it in the book. But now here is a question for you. There is a hoop. So all the masses, most of the masses, see these have negligible masses here on the spoke in this wheel. Okay, those are spokes. Most of the masses are here. So mass is same for both of them. Radius is also same for both of them. But for this, some masses are closer, right? And some masses are at the same distance. But the total mass here is concentrated this distance r over here. But over here, what we have is that the mass is distributed all over the places, including this axis of rotation. So rotational inertia for the mass very close to this gonna be very small, and the masses that is very far here gonna be the large one. But for all of these, rotational inertia gonna be this chunk of mass, this chunk of mass, this chunk of mass. If masses are equal, rotational inertia gonna be equal for all of these, so we can add them easily. This one gonna be little tricky, but I want you to think using this idea and tell, not, you don't need to tell me the formula, but which one gonna have larger or smaller rotational inertia, okay? So you have a minute to answer this question. Thirty more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. So which has larger? We are looking for the larger one. So hoop. So that is correct answer. So in this case, hoop has rotational inertia, for example, I. So if we have like n number of masses, m1 r1 square, but the r is same for all masses, so m1 r square, m2 r square, m3 r square, and so on. So if we just add all of them, we're gonna get r square factor, And then we're going to have M1 plus M2 plus M3 and so on and so on. So this whole thing is the total mass. So that's why it is just mr square. That's the for hoop or ring. Okay. So that's the rotational inertia, mr squared. How about disk? So disk has a smaller because these masses are not at the same distance for all of them. See, the one that is there, they are at a smaller distance. The one that are there, they have zero. See, distance is zero means rotational inertia is zero. So in a whole, in the merry-go-round, if you are standing right on top of this, at the pivot of rotation, what happens is standing there is a lot easier for you than standing all the way there in the disk. Okay. So rotational inertia for the mass, that's all concentrated. So if all masses were concentrated right there, then the rotational inertia would be zero. And we just learned if the masses were all concentrated at r distance, then that would be mr square. So we can say, okay, I for the disk is the average of, okay, this is the kind of simplest way of looking at it. So that gives me half mr square. So for the disk, so when mass distributions everywhere, rotational inertia becomes smaller, and turns out in this case it becomes exactly half. Okay. And if we have a sphere, for example, ball, right? Round ball, and the ball could be empty inside. Some balls are empty, for example, soccer ball, basketball, you put air inside, right? So they are empty from inside. So all masses are at this distance r on that sphere. Okay. So a sphere can be hollow, or solid. So if they have same mass, so I'm making clicker question here, okay? If two spheres have same mass, but one is solid and the other is hollow, which has larger inertia, rotational inertia, okay? Which has larger rotational inertia. Let me just write I here to make it shorter, okay? So hollow sphere, solid sphere, or both of them have same rotational inertia. So now I'm pulling on this question, folks. Hopefully you are paying attention. And you have 30 seconds to answer this question. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got. Hollow, just like before. So since masses are far, means it's going to have larger rotational inertia. So that makes sense. Okay. And you can find the rotational inertia of spheres in the book. I think one has 2/5, another one has 3/5 mr square. So now so I like this problem because it has both kinematics and dynamics for the rotational motion at just one problem here, okay? So first, let's look at what's going on. Two children standing in opposite side of merry-go-round are trying to rotate. So you can see one kid is there, and kids are smarter. They've been doing this for long. So they know one kid has to push that way, another kid has to push that way to get it rotating, because both of them gonna form the, the torque gonna add up if they push something like that. Opposite side direction from the opposite side makes the torque in the same direction. So we can make free body diagram of this one, something like this. So one person pushing something like this, another person pushing something like that, and it is pivot over there. So it makes sense to, and this force and that force, both of them are same. So rather than writing F1, F2, I'm just writing F here. And just like I was saying, pivot is here, it is rotating about that point. So that's why it makes sense to use this as the axis of rotation. So radius is like that. Okay. So that means lever arm, in this case, going to be R for both of those forces. So that's what's happening here. So how much is that? 2 meter, and force is 10 Newton each. So in part A, it is kind of a kinematics problem. If the round has a mass of that much, so mass is 180 kilogram and radius of 2 meters. What is the angular acceleration? Alpha is what? Okay. So here they start from the rest. So initial speed we can say 0. Now we don't have acceleration, we don't have time and so on for this part. Okay, time, acceleration, they are not there. So maybe it's not a good idea to use kinematics. But maybe you can use dynamics because we have, we are looking for acceleration and there is rotational inertia and the forces are there, means we can find torque. So maybe you can use, so this is disk, so the rotational inertia for the disk is half mr square. So mass is known, r is known, so that means that is known. So to find this, since we know rotational inertia, we can use sum of torque is I times alpha. So alpha is sum of torque divided by I. So I we know, all we need is sum of torque. So how do I find sum of torque here? So torque due to one force is R times F, and torque due to another force is also R times F. Remember, force is still perpendicular. Kids are smart. They know which way to push and get the best result, okay? So they are pushing something like that. So that's perpendicular to the radius. So that means torque due to one force is RF and torque due to another force is also RF, okay? And rotational inertia of the disk is half mr square. So now you know everything, means you know this, or we can cancel one of the r, so 2f, and remember there is also r, 2fr or 2rf, maybe I should write rf. And then there is this half, so fraction of fraction goes top there and multiplies 2, and there is mr square. So one of the r cancels, giving us 4f over mr. So this is easier to do arithmetic than this one here, but of course you can just do it here, okay? And the unit gonna be radian over second square for this one. Now for part B, it is asking how fast the merry-go-round is rotating after 4 seconds. So omega f is what? Given the time interval is 4 seconds. See, now time interval is given, and we also found the acceleration here for f over mr from part A, right? And omega I is also known because it, of course, it starts, it does not say with what speed it was moving when kids started pushing. So it must be at rest when they started pushing. So we can say omega I is 0. Okay. So time information is there, and alpha is there. We are looking for final speed. Initial speed is known. Final speed we are looking for. Time interval is there. Acceleration is there. So that means we can use this formula. Very fast formula in the list. Okay. So omega f, so this is 0. And alpha is, if you have number, you can use that without rounding here. Since I don't have, I'm just using this. Oh, that was for alpha, yes. Alpha times t squared. So delta t squared or just t squared. I think I wrote, what did I write for the time? Delta t. So let's write delta t squared. Okay. So 4 times 10 times 4 square, and then m, that's a huge 180 times r is 2 meters. Right? And looking at all these, it looks like 2 sig fig problem. Okay, so you can round it to 2 sig fig. Okay, it looks like it is 32 over 9, and the unit of final speed would be radian or second. And of course, you can find the number here or just do this. Okay, so I think it's close to 3, so it's 2 point something. That looks like we are getting here. Okay, radian per second. Okay, so that is kinematics and dynamics. And we also learn how to do rotational equilibrium. So we learn a lot of things today in this class. Okay, and next, from kinematics, dynamics, it goes towards the work and energy, conservation of energy, and then momentum and conservation of angular momentum. So next class, we're going to focus on that conservation of energy for rotational motion and conservation of momentum for the rotational motion, okay? So this is going to be whole thing, review of whole thing that we have learned so far in the semester, just in one chapter. Okay, so I'll see you next class, folks. And remember, second midterm is coming soon. So keep that in mind as well. And I have posted new worksheet. So feel free to ask question if you have any, or else I'll see you next class. And I also have Zoom hour today later.